Okay, so here's what we've got today is, and it would be handy if you wanted to play along. That sheet of thermodynamic lecture notes that I gave you, it's got a whole bunch of words, saying system, all this good stuff. The heart and soul is on the back. And there's three types of processes that we're going to go through related to what you can do with the gas. So if you look at it like a simple syringe, okay? So if you look at what we can measure and then what we can infer from that. So we're going to start off. I'm going to give you a certain number of moles of gas, which is 0.1 moles, which isn't very many. Oh, I'm not in the mood for you today. I'm talking about pen, by the way. Not Cohen. Moles. Okay? So what this graph will allow us to do is keep track of pressure. This is going to be huge. This only works if it's in newtons per square meter. And then on your x-axis, you're going to have volume in cubic meters. So it's weird because you'll see that this is almost like a three-dimensional graph, because anytime you have pressure and volume, and assuming that you know the number of moles, you can also find the temperature that corresponds with that. So what we're going to do is we're going to look at how you can change these different variables of pressure, volume, and temperature. So temperature, basically you take the thermometer, you put it in there. We've arbitrarily chosen a scale that says, hey, you know, at 273 Kelvin, water is going to freeze. At 373 Kelvin, water is going to boil, okay? And the temperature basically is you're measuring, it's like the radar gun on an atomic level. How fast are the particles moving? Volume, pretty simple to measure. Boom, hey, what's the volume inside the syringe? The pressure sensors, is what you guys are going to use for lab tomorrow, is basically how that works is that within this pressure sensor, there's a little valve right there. And basically what it does is that it senses how many particles are bouncing across that surface, and that translates into a number. And we say, oh, that's 100 kilopascals, or 1 atmosphere, or whatever that number is. So what this graph allows us to do is keep track of three different processes, what we call isovolumetric, isothermal, and isobaric. So if you look at the word iso means the same. So if you ever study meteorology or you study weather, one of the things you focus on are what are called isotherms. So isotherms on a map are lines of equal temperature. Isobars are lines of equal barometric pressure. And the closer those if you look at a map and you want to find really, really strong winds, find isobars, lines of equal pressure, that are really, really close together. Because that shows you if they're really, really close together, there's a huge pressure gradient, and pressure gradients is what creates wind. So when you look at these things, understand that iso means the same. So if it's isothermal, and that's the first one that we're going to go through, that's the most complicated one, because we're keeping temperature the same. Then you can have isobaric, means that you're going to keep the same pressure, and then you can have isovolumetric, meaning that we're going to keep the same volume. Okay, so we're either going to keep temperature the same, we're either going to keep volume the same, or we're going to keep pressure the same. Okay, so that's what ISO means. So on the back side of those lecture notes, I've kind of got a summary of what those are. Now, on that purple sheet that you have, there's going to be a section of thermodynamic values. So if you look over here on this thermal physics, okay, so we've already talked about pressure, force divided by area. We'll get into Q over delta T. That's what we talked about in terms of that's a heat row thing. So today we're going to talk about this equation here where you have 3/2 nRT, and then work equals negative P delta E, and then delta U equals Q plus W, and you've got Q equals MC delta T. So here's the story. So we're going to take a gas containing 0.1 moles, okay, not an entire mole, 0.1 moles. We got a temperature of 20 degrees Celsius, and we have a volume of 0.1 cubic meters, okay? And we're gonna figure out what that pressure is, because we've got to have that value to put it onto this graph. So, it's coming off the weekend, I'm assuming you all might have forgotten everything that I might have taught you. So, we know the moles, we know the temperature, we know the volume, we need to find the pressure. So you know that PV equals nRT. So Danny, I need to get pressure by itself, what am I going to do?
Divide by V.
Divide by my volume, that is not velocity, okay? Not velocity. So I got 0.1 moles. We're going to do the ideal gas law constant of 8.314 joules per mole Kelvin. Now, the temperature is 20 degrees Celsius.
293.
293. Do not leave that as Celsius, because if that's wrong, everything is going to be wrong from here on out. And then we have a volume of 0.1 cubic meters. That makes that simple. Those numbers cancel out. So somebody take 8.314 times 293.
2,436.
2,000 what?
440.
Newtons per square meter. So we're going to come over here and go, okay, we'll call that like 2.5. So we're at 0.1 and 2.44 pascals. Okay? So here's why this is like a three-dimensional graph. If you know the pressure and you know the volume, assuming you know the number of moles, then you can figure out, hey, what's that temperature going to be? So at any point, this is going to be important when we go through these calculations. You know the pressure and the volume, you can always find a third point of temperature. So here's what we're going to go through first. We're going to go through what's known as an isothermal expansion. So when you look at what I can do with this syringe, okay? So what we're going to do is I'm going to take this from like 0.1, and then I'm going to pull that back. I'm going to increase the pressure. So from a classroom perspective, and by the way, tomorrow I have to go and read my book to a bunch of first graders. Pray for me. I'll do that during second block. We'll talk about that tomorrow. But so imagine that you have a group of second graders. Now, so it's isothermal. That means we're not going to change the number of Skittles involved. Okay? We're not going to change the number of Skittles. So basically what we're going to do is we're going to take the classroom and we're going to make it bigger. Okay? So keep in mind how this pressure sensor works. This pressure sensor works by collisions. Okay? And it measures two things in terms of the collisions. How many collisions that there are, and how much energy there are in the collisions, okay? So to make the pressure go up, you either have more collisions or those collisions have more energy. The particles are going faster, okay? If you drop the pressure, you either have fewer collisions or the collisions have less energy. So here's what we're going to do. So we're going to take this thing from an initial volume of 0.1, and we're going to go out to 0.5. And we're going to keep the temperature the same. So here's the other way that you can look at this. You've got PV equals nRT. So because you're told that it's isothermal, this entire right side of the equation is not going to change. Okay? I'm not going to change temperature, I'm not going to change the number of kids in the classroom, and I'm not going to change the gas law constant. Okay? So the inert side of this equation is a constant. Okay? It's constant. I don't know what it is, I don't care what it is. I just need to know that it's a constant. So, mathematically, Will Stanley, I'm gonna make the volume go up.
Okay.
And I still want the same NERT. So what's gonna happen to my pressure?
It's gonna decrease.
It has to go down, right? So this is gonna be an inverse relationship between pressure and volume. So basically, if you imagine that group of kindergartners, okay, second graders, pick one, they're all little ankle biters.
Timmy's.
And we're gonna keep the same number of kids, we're gonna keep the same number of Skittles, but we're gonna increase the size of the classroom. So what's gonna happen to the number of collisions with my ankles?
It's gonna.
You're gonna go down, pressure's gonna drop, okay? So,
Just move your feet really fast towards their head. They tend to steer clear.
Gap
of that
Sean.
pose for a little while.
just a generic way, what does an inverse relationship look like? A simple inverse relationship look like on a graph? Something like this,
Yeah.
okay? X gets value, gets bigger, Y gets smaller, okay? Simple relationship. So that's what we're going to have here. So we're gonna take this line all the way out here to 0.5. So that's gonna be a curved line like this, okay? Now, what's gonna be important is that this is not a straight sloping line. This is not going to be a triangle, okay? It is not going to be a triangle, but let's talk about area.
Calculus!
Well, we'll get into that, okay? So, if it had been a horizontal line,
These trapezoids.
okay? If it had been a horizontal line, you could find the area, simple, right? It's a rectangle, right? So what units would you end up with if you were to find the area underneath that line, assuming that that pressure is in newtons per square meter, and that volume is in cubic meters,
Meters.
otherwise known as,
Joules.
or which is otherwise known as,
Energy.
or work, right?
Sorry.
So here's what's gonna be important. The area underneath this line is gonna represent work. Okay?
That seems important.
It's muy importante. Okay?
See.
Yes.
Gee.
Okay? Now, we'll get back to that. So there's a couple of other equations I need to float out to you. So I find this odd that you have this U equals 3/2 nRT. Most of the time that's actually, I've never seen it written like this. Most of the time it's written as delta U equals 3/2 NR delta T. Now, let me explain what U is, okay? U is the sum total of all of the energies that exist within the system. So imagine if you have a room full of second graders, okay? There's all these different types of energies that you could have. You could have Timmy doing cartwheels. You could have Timmy sitting in chair doing this like, whee, okay? You could have Timmy bouncing off the walls. You could have Timmy sitting in the corner going, sup, okay? You're not doing much. So, but here's what is going to be important, is that delta U, the sum of all the energies, is one of the most important concepts in all of thermodynamics. But we have no delta U probes, okay? Will can't come up to me and say, hey, Brookcamp, hook me up with the delta U probe. Got nothing, okay? It's one of the most important concepts that we have, but we cannot directly measure it. But here's what we can measure. So if you look at this, this is 3/2. That just comes from the statistical thing, okay? Just don't worry about the 3/2, just accept it. So then you have N, which is going to be what, Sean?
Moles.
Moles, okay? Then we're going to have R, which is going to be the gas law constant. Again, you have to use 8.314 joules per mole Kelvin. Now, again, this is changing temperature, okay? This is not temperature. This is change in temperature. But that's still going to be in Kelvin. So the moles cancel out, the kelvins cancel out, you're left with joules, okay? Now, here's where this is important. If the temperature doesn't change, what's the value of delta U?
0.
0. Guess what? This is going to be an isothermal expansion.
So
What's going to be the value of my delta T?
0.
0. So therefore my delta U is going to be
0.
cool. Okay. Now, delta U also equals, if you look on here, okay, delta U also equals Q plus W. Now, Q is the thermal energy flowing in and out. So if I have this syringe, okay, the Q value is going to be one of two things. It's either going to be how much energy that I put in. So let's say, like, you might take this syringe and put it into, like, a boiling glass of water, okay, a hot plate, right? Heat water, water bath. So if that's the case, and this is all about the signs, if Q is a positive value, that means heat is flowing into the system. Now, if you think about it, that makes sense. So Q is like the Skittles value, okay? So if you have a positive Q, and remember, delta U is the sum of all the energies. Don't worry about work for now. We'll deal with work later. So I walk into this kindergarten class tomorrow, and I say, hey kids, I'm going to read you a really cool book, but I'm also going to give all of you a bag of Skittles, okay? Teachers are going to hate me.
What size of bag?
Huh?
Are you
Doesn't
talking
matter.
the
Like a little individual.
Okay, yeah.
Okay.
Are you actually gonna do that?
The
No.
fun size.
No, because otherwise they would hate me. Yeah, I wouldn't do that to them.
Start the
So
Skittles.
here's the story.
I will
So
give
if I
Skittles
gave
to my
each of those
team.
kids a bag of Skittles,
Skittle squad.
in addition to reading the book, what?
Turn this into a fundraising opportunity. Threaten them. Say you'll give the kids Skittles if they don't pay you.
Yeah, that's
Extort them.
No. So it's like money from the solar fund, or I bring Skittles. You decide.
I'll just scatter Skittles around the classroom just by the
Yeah.
fistful.
Or better yet, I'll tie it to a puppy and turn the puppy loose. That'd go well. So again, if you have a positive Q, that means Skittles is flowing into the classroom. What's going to happen to the total energy inside that classroom? It's going to go up. Okay? Now, the other side of that, the teacher gets back to the classroom and she goes, all right, give me all the Skittles. I don't care what Mr. Burkham did. Give me all the Skittles. So if Skittles flows out of the system, if you put it in an ice bath, the delta U is going to go down. So this is a lot of thermodynamics is understanding the concept of prepositions. So if you're told that energy flows into the system, okay, or heat is added to the system, Q is going to go up, delta U is going to go up. So oddly enough, if Q is a negative value, energy is going to flow out. Okay? That's it. Energy flows in and energy flows out. Now, the other side of this is the value of W, which is going to stand for work. Now, this is where you have to go old school. Okay? If you remember the very, 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 very first definition of work when we started to talk about work, what were the two criteria that had to be met for work to be
Force over
done?
distance.
Had to be a force, and it had to act over a
Distance.
distance. So, if I just hold this syringe right here, I'm not doing any work. But if I push in on this, I do work. Why?
Force over distance.
I do a force over distance. If I pull back on it, work is being done. Okay? So if you change the volume, you do work. Okay? Now, work, oddly enough, could be positive or negative, depending upon the situation. And that's what we're going to go through in terms of the algebra in just a second. So, actually, it's the calculus, but we'll get to that later. So, here's the basic idea of work. Work can be positive or negative, depending upon if the volume is getting bigger or if the volume is getting smaller. Okay? Cool with that. All right, so I've got this syringe, okay, and plunger. Get that down towards the bottom. Come on. Okay, there we go. All right, so close this up.
That makes the spark.
Okay, so
We should hit the lights.
I'm going to
so they can
slowly
see.
push down on the handle. Now, when I do that, am I doing work?
Yes.
Yes.
Why?
Force over distance.
Force over
To
distance,
change
right?
the volume.
What am I doing to the volume?
Changing it.
Decreasing.
Changing it but I'm making it
Smaller.
smaller.
It's different.
Yeah, who wrote that on their paper? Oh, there was a kid in my fourth block class.
Deacon?
It was that question about the expansion joints. Used the word different 3 different times in the sentence.
Was it Deacon?
Yeah, it was actually. How'd you know? Yeah, it was Deacon, actually. Okay,
You can just tell.
now,
Our second guess would have been Charles.
Charles wouldn't go through that much work. He wouldn't write, that's too many letters from Charles to write, especially 3 times. No.
Yeah, Charles would not be doing that.
No. Okay.
Charles was too lazy to do
Yeah,
that.
speaking of different, there's Charles. Okay, so, now I push down on this. And the pressure is getting
Small.
Bigger.
Bigger.
bigger. Why?
Because volume's decreasing.
Volume.
Volume
Right,
smaller.
okay? Now, when I let go of this, what's gonna happen?
The pressure will go up.
Return to the screen will return to equilibrium.
Now, so now if you think about this, it's kind of cool because what's holding this plunger down?
The atmosphere.
And
Gravity.
gravity. So these little particles that you can't see, okay, it's magic, right? I push down on them and you can't see them, but I'm compressing them. Now, if they liked this state, what would happen?
Stay
They would stay there. I would take my hand off and they'd go, it's cool, right? Like this. You know, close
Right.
together, like that. But they don't. So when they expand, they have to push against the atmospheric pressure, and this is a heavy steel rod. Okay, this has some weight to it.
Some good.
So when that expands, okay, that goes up. It's got to push, even if you don't have an atmosphere, you still have to push against gravity that's trying to hold that down. So now, this is where you can tie this into humans. If I said, okay, there's the 6 of you. I want all of you to stand really, 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 really close together into a very condensed area. Okay? I think you all like each other, and you'd like, no. Okay? Not digging it. And then I say, okay, you can go back to your seats, and you all would not stay like that, right? You all would be like, oh, we're out. Okay? And everybody's going to go back to their seats because that's where you're most comfortable. And so when I walk in this room every day, one of the things I don't worry about is all of the particles of oxygen and nitrogen that make up the atmosphere of this room. I don't worry about over the weekend, they all go hide in the corner. Okay? It's like, let's play a trick on Burkamp. Let's make the room a vacuum and let's go hide in the back corner. We'll show him. Okay? And I walk in and it's a vacuum on, blood boils and bad things happen and I can't breathe.
Doesn't your head explode?
There'd be so many things that would go south. So,
We haven't quite
most
done
importantly,
enough.
my blood would
That's
stay
data.
as they begin to boil. Because you have dissolved
I don't know
oxygen.
enough
Oh,
Humans
no, that's the, if your diving suit fails, like those deep sea diving suits,
Yeah.
if the pressuring system on your diving suit fails, your entire body gets collapsed up into your helmet,
Yeah, that
Yeah.
does happen. Okay,
which is
stop.
bad.
So, that's one of the things I
What a
don't
great
worry
thought.
about when I walk in the room.
That's just what-
Oh, have all of the particles in the room gone to the back?
Yeah.
No, because of the fact that they like this equilibrium, they like to be spread out. So, to force that, requires work. But then when you take your hand off, they go, we're going back to where we did.
Senior prank.
Now,
Volume particles.
yes, you're back.
Remove all the air from the
Make
school.
the school a vacuum.
Yes.
Problem is, you couldn't get the doors open if you did. Okay, so now I'm going to do this, but now I'm going to do this rapidly. Okay, I'm going to do this rapidly.
Airlock system.
So what I want you to do is focus on what happens to a piece of cotton in the bottom. Okay?
There's a piece of cotton in there?
Yeah, it's just a piece of
Oh,
cotton.
I see now.
Okay?
Oh.
Part.
So when I did that, what happened?
It
ignited.
It caught fire. Okay?
Yay, yay.
I made fire. So basically what happened is this. I did that so rapidly, and the particles flipped out so much
Temperature.
that it created so much kinetic energy, because they were all flipped out, that was enough to catch that cotton on fire. Now, if I did the same thing slowly, it didn't happen, because of the fact that if I did that slowly, there was an increase in energy, because like you all don't want to be together in a very, very condensed area. So if I said, okay, hey, kind of stand up and move around, all right, you guys would do it, but it would allow you that thermal energy to escape. But imagine that I could just, boom, smash you all together. It's like, oh, sorry, Cohen caught on fire. Okay? Okay? It's okay. It's just a flesh wound. Okay, Cohen's better. So,
Tis but a scratch.
it is no scratch. So, what I did there, and I did work because I compressed the system, but I did that so rapidly that it caught on fire. So this is how diesel engines work, okay? So diesel engines don't have a spark plug, because diesel engines take diesel fuel, oddly enough, and they have a very, very high compression. And they compress that fuel, and once they get it compressed, just like that cotton did, it ignites, boom, drives that piston back down. Okay. All right, so here's what I want you to see. Delta U equals two things. It equals 3/2 NR delta U, and it also equals Q plus W. So what we're going to do is we're going to move this thing out here to 0.5 meters. So here's what we're going to do. I need to find that new pressure at that point. Okay, Cohen?
Yeah. Sorry, I was showing them a really funny shirt. You want to see it?
No.
I'll just describe it then. It says it's tis but a scratch, but he's at a turntable and he's missing his arm. He's got the scratch discs. I thought it was funny. So I know someone who owns the shirt, so I was showing it to them.
Okay.
Specifically at night.
Yeah, it's
Yeah.
from.
Okay. All right. So here's the whole key to this. What am I holding constant? Temperature. Okay, the NRT part.
Isothermal.
So when you find this new pressure, it has to be less than the 2.44 times 10 to the third, right?
Yeah.
Okay, right? So it's just like we took this and we pulled this out, okay? So I need to find that new pressure. So how can I do that?
Math.
Math.
Calculus.
That narrows it down. So you know that P1 V1 over T1 equals P2 V2 over T2. True?
Indeed.
But it's isothermal.
So you get rid of the T's.
So I don't have to worry about the temperatures, right? Okay, those are gone. Okay, that's, by definition, that's what isothermal is, same temperature. So I've got my pressure 1, which was 2440. My initial volume was 0.1. Gapchons, find me that new pressure, because that new volume is 0.5.
So you divide by point.
Yeah, so basically 244 divided by 0.5, which should get you 488.
488, yeah.
Okay? So,
The meter is cubed, not the 0.
yeah. Okay? So,
Meters cubed.
is that right?
I don't think it's.
I don't think that's right.
Krishan, speak
It's
up.
488.
488.
Yeah.
Okay, yeah, it's like, whoa, something's wrong. Okay?
This
Double
math
the-
ain't mathin'.
Yeah, I was gonna say, whoa, this is bad, I broke physics.
Physics
Okay.
is broken.
Cool.
There's a secret
Did
spot.
it again.
Now, again, that's actually a very, very low pressure. It sounds big, but if you consider normal atmospheric pressure is 101,300, that's like 500. So that's actually a very, very, very low pressure.
What's Mars?
Huh? Oh, I can't, it's like a tenth of our atmosphere, so if that. All right, now,
This is basically just rock.
here's the next part of the story. So, we've got this action here. We've got 0.1 cubic meters. We went out here to 0.5. So on that sheet of lecture notes on isothermal, I've given you this equation. It's work equals nRT, and then the natural log of volume initial from volume final. It's on the back side of the lecture notes. There's the
log.
It's natural log. I think it's VI. It's VI over F. I think.
Yeah, VI over VF, yep.
Yeah. Okay.
Stay the semester.
So the reason that we have to do calculus, and if you ever need this equation, I will give this to you. Don't memorize it. I will give this to you.
Oh, one
Okay.
over U.
So because of the fact that it's a curved line, and if you go through the calculus, you can end up at this point. Now, here's what's important. This only works with isothermal values. Why?
Because the temperature is the same.
Yeah, if I change my temperature right away, I can't do this because I don't know which temperature to use. Now, N is going to be the number of moles. Now, the R is just R. Temperature has to be in Kelvin. Now, when you look at this natural log, so let's have a quick refresher of natural logs. What if my volume initial is the same as my volume final?
0.
0. Okay? So guess how much work is done?
0.
0. Okay? So this equation produces a value of 0 if your volume initial and your volume final are the same thing. Okay? So, in this situation, we're going to take 0.1 moles times 8.314 joules per mole Kelvin. And then the natural, now don't touch a calculator, do not touch a calculator. Now in this situation, my initial volume was 0.1 cubic meters, and my final volume is 0.5 cubic meters. Okay? Step away from the calculators, step away from the calculators. I'm going to basically be taking the natural log of 1/5. So when you take the natural log of a value less than 1, what's the sign?
Negative.
Negative. So I'm going to have a work value that's going to be a negative number. Okay?
You're shrinking the.
Because now, so work's going to be a negative value. Volume is getting bigger. Okay? Work's going to be a negative value. And here's the reason why this works out. Imagine that we'll take Cohen, for example. Okay?
Yay.
And we're going to wrap Cohen in saran wrap.
Cool, okay.
No.
I don't need air.
Nick it down.
Aw.
Sorry. Now, Cohen hates being wrapped in saran wrap, and who could blame him, right? So, Cohen is going to flip out. What's hey, we get it. We get it. Stop.
That was my Charles
Do I have
impression.
permission to like kick him under the table?
No. No.
Yes,
Now, Cohen,
Yes.
when you make your volume bigger, does that cost you energy?
Yeah.
Yeah, because you got to rage against the machine, right? Okay? So, what's happening is if you could see this happening, you would see, if this was your syringe, you would see that syringe being pushed out. Okay? You would see the system getting bigger. Now, this obviously only works when you have a system where the volume can change. We can't do this with Will's thermos because that's a fixed volume. Okay?
You could dent it.
Really, probably not what we want to do.
Yeah, not really.
So this is going to be important. This is only going to work
I don't know.
when we
Probably
can
there,
change the volume. If it's a sealed system, this won't work. Okay? Now, somebody do the math. Take 0.1 times 8.314 times the natural log of 0.1 over 0.5.
Negative 1.34.
No.
Negative 1.334.
Negative
What'd
one
you-
point.
hold on. I left out the temperature part of it. My bad.
Oh.
Multiplied
I
by.
was like, something's wrong. That's too small a number. Times 293
Negative
Kelvin.
392.
I left out the temperature part.
Negative 392.1.
That I can live with.
That's a lot of
Negative 392.
joules.
I'm going, whoa, something is bad here. You
No.
broke physics.
Yeah.
Okay.
Huh.
No. Boiling water takes a million.
So
Yeah.
what this represents
Remember
is
that ping
the
pong ball at like
area
20?
There's
underneath
a ping pong ball.
that line. Okay?
This is air. You could heat up one
Now,
molecule
this
of
is
water.
where it goes big picture. Okay? So, if you go back up to these first sets of equations here, what is delta U going to equal?
0.
Something.
0. Why?
Because it's an isothermic.
So there's no change in temperature.
Yeah.
So if delta U equals 0 coming out of this equation, guess what? It still has to equal 0 coming out of that equation.
So there's 0 work.
So if my work, which we just found, was negative 392 joules,
Not 0.
Then you need to put 392 joules on.
oh! That means my Q value is going to be 392.
Otherwise, you're just
joules.
kind of destroying energy, which is
Yeah.
frowned upon.
Well, it is. So here's
Circles.
what's going to happen in terms of a visual. To
Eventually,
make
it's
this
gonna
happen,
be
would I put this thing into an ice bath or into a hot water bath?
To what?
What?
Was
Hot
it
water
like-
bath.
To do this particular demonstration,
Hot bath,
Oh.
because you need to
Why?
add joules.
I got to put energy into it.
Q has
right?
to be big or
So
positive.
I'm going to put energy in. Well, what would you see the syringe, the plunger do?
Expand.
You would see it expand. So the energy that goes in doesn't change the skittles. So what I would, in this situation, if you imagine me reading my book tomorrow. So I'm going to walk in with these kindergarten kids, and I'm going to say, all right, kids, we're not going to give you any skittles, but I need you to make the room bigger. So there would not be any net change. So I would actually have to give the kids some Skittles. But I would say, what are you going to do? Now you've got more energy, but now we're going to make the room get bigger. So I'm going to say, teachers, I'm going to give the kids Skittles, but I'm going to put them to work. Okay? And we're going to push on the walls of the classroom, we're going to make it bigger, so there's no overall net change. Okay? So you can also look at this in terms of like human interactions. Okay? So I write my will and I'm going to say, okay, to go and hire, I leave the sum of $50,000.
Yes!
That's the Q value.
Why does Cohen get any?
But I'm taking $50,000 from him.
But Cohen doesn't get to keep the money. Cohen has to do work with the money.
I'm okay with that.
Cohen has to somehow make the world a better place.
Deal.
Okay?
Deal. I'll make
I'll
my
leave
world.
you, I'm gonna leave you 50 large, okay? But you have to do work with it.
Whose definition of making
Yeah.
the world a better
Yeah, you really need to
I'm-
define better.
That's up to you,
Ooh, less people.
okay? What?
I said less
No,
people.
come on, no. No,
Moving drugs from the market.
less people is not an option, okay?
Competing with the
Ooh,
No.
I turn it into
Build an orphanage, put solar panels on something, you know,
pay for my college to become a doctor, then I can help people.
okay, that's
Is
fine.
that good enough?
That's, that's a stretch, but anyway.
Have majority ownership in the
Okay,
cartel.
now, so here's what I want you to see.
Would you take insurance?
So on this line, when we're going from here down to here, what was the sign of Q?
More than zero. Positive.
Slow
Right? We had to dump energy into it.
stuff, Cohen.
But what's the sign of my work?
Negative.
Negative. And when I add those values together, I get
Zero.
0.
Otherwise, you're making the energy.
Okay? Now, if I reverse this, so once I get it expanded, if I wanted to go back to there, what would I do?
Positive.
Ice bath, hot water bath.
Hot water bath.
Ice. You're trying to get it back to normal.
I'm gonna try and get it back to point 1.
You gotta take those theoretical Skittles away.
Yeah, I gotta take the Skittles away,
Take
but
all the
now,
Skittles away
here's
from
the story. Look at this, then what happens in terms of that work calculation.
Not a single
Here?
Skittle in the whole world.
Now, I'm gonna have 0.5 over 0.1,
Which is positive.
which is a positive value. So now my work would turn into a positive value. So here's what I want you to see. In terms of work, okay, if you increase the volume, work is gonna be a positive or negative number.
Negative.
Negative number. If you decrease the volume, work's gonna be a,
Positive.
now, so, because things don't like to be expanded. And so, when they expand, it costs energy. So here's the classic way to do this. So if you put your hand in front of your face and blow on it with your mouth open like this, how does it feel?
Warm.
Warm.
Toasty.
Now do the same thing, but then pucker your lips and then blow on it.
Cool.
Feels cool. Okay? Why? Why does it? It's the same air.
Because the volume for one's way bigger, and the volume for one's smaller, because it's in like a small cylinder and a big. I don't know.
The speed.
Area. I'm just gonna say
What do you
buzzwords
have
until
to
somebody
do
hits.
when you pucker
Oh.
your lips? What do you
It-
have
Oh,
to
your
do?
Increases
your
the
left-
pressure,
Your left volume
and then
has
it
cold air.
expands.
Oh!
Decreases when
You
it,
got to compress it,
when it
right?
comes out.
Was.
Or your left lung has cold air.
Oh,
Right.
shush. Shush. So, Will was right. What did you say, Will? And don't give me the left-right law theory.
You have to increase the pressure when it gets.
Do you do work on it?
Yes,
Yes. Why?
There's a
because
force.
you're increasing the pressure
And decreasing the
volume.
volume. Okay.
And then,
And
when
then once it gets past that, what does it do?
then it returns to normal and increases
It expands, returns to
Yeah.
normal, and that costs
Energy.
energy. Okay? So that would be like us wrapping up Cohen in saran wrap. Okay? That's like puckering your lips. And then when Cohen gets free, that costs energy. So let's say that you're given a bowl of hot soup and you want to cool it down. You want to cool down the soup. Are you going to blow on it like this? Or are you going to go,
Hey, the good old stern blow is a famous soup cooling method.
I'm gonna
Shut
do
up,
it. Go.
just stop going. Okay, cool with that. All right, stop the camera. I know you've been sitting. Stand up, take a stretch.